Hi, my name is Amy and I'm a PhD student here at UNSW in the Atomic Physics group. Atomic physics is the study of atoms, in particular, the energy levels and the behavior of electrons around the nucleus, and also the study of phenomena which affect these electrons. I am currently working on theoretical calculations of isotope shift. We have all heard of atoms consisting of electrons in well-defined energy levels around the nucleus. If we shine light on this given atom, then the electron can absorb a photon of the correct energy and jump up an electronic energy level. In the same sort of way, the electron can emit a photon of equal energy to the spacing in the energy levels on the atom and jump down an energy level. Now, if we collect all of this emitted light from the atom, we can produce what is called an atomic emission spectra. And this spectra is very particular to our given atom. If we compare the spectra of an atom, for example calcium, with a proton number Z equals 20 and a neutron number also equal to 20 to give an overall number of 40, with one of its isotopes, for example a neutron number of 22 to give 42, and look at spectra from both of these isotopes, we notice that even though these atoms are exactly the same atom, they have slightly different spectra. So the overall shape of the spectra looks the same, but some of the transitions are shifted slightly in energy, and this is known as isotope shift. Isotope shift comes from the fact that you're adding neutrons into the nucleus. You are changing the volume of the nucleus, and you're also changing the mass of the nucleus. This respectively changes the charge radius of the nucleus and the way that the nucleus moves in relation to the electrons. So isotope shift calculations that I am doing are very interesting because we can use this isotope shift phenomena in the search for new particles beyond the standard model. We are currently trying to come up with a recommendation for which atom to use in isotope shift experiments. We are trying to find which atom will be best for finding the effects of new particles within the nucleus. But this is not the only cool application of my work. Isotope shift calculations can be used to search for the hypothetical nuclear island of stability. So if we go above, say, lead or bismuth in the periodic table, we find that most of these atoms aren't actually stable. They all undergo radioactive processes such as alpha decay or emitting beta particles, etc. So a super heavy atom is an atom with about 100 or more protons in the nucleus. Now it has been proposed that if we have super heavy atoms with an isotope with neutron number of about 184, which is a lot of neutrons, that these particular isotopes will be stable or relatively stable. But there is a catch. We currently can't produce these isotopes on Earth. That's because we currently use colliders to smash together lighter atoms. And these lighter atoms don't have the neutron to proton ratio needed to create these neutron-rich superheavies. So where do we search for them? Well, in astrophysical processes such as supernovae or neutron star collisions, we see a high neutron flux, so lots of neutrons whizzing about. And this is the sort of environment which facilitates the production of super heavy atoms. So there might be a chance of these super heavy atoms existing in stars, and luckily we can read the spectra of stars. If we can measure the spectra of our neutron deficient isotopes of super heavy atoms that we create on Earth, and pair this with theoretical calculations of isotope shift, we can predict what the spectra of a stable super heavy atom would look like. And therefore, this will help us search for stable isotopes in stars. I really enjoy exploring the theory behind experiments, and I hope that my small contribution to the theory of isotope shift will lead to discoveries such as new particles in the nucleus and the discovery of the nuclear island of stability in astrophysical spectra. I chose to do physics primarily because I enjoy it. I really love the problem solving and also the fact that there's always a new challenge to overcome and something new to learn.